Hello, I'm Weiwei. I work on the Mojo language team at Modular. Today I'm going to talk about parallelizing the LLVM pipeline with MCLink. So this talk is in the context of Mojo compilation, which we've already discussed about in last year's LLVM dev meeting about how the whole compilation pipeline look like. So today I'm going to mostly focus on the LLVM part, mostly zooming into some of the implementation details that we are doing to parallelize the LLVM part with the help of MCLink that give us both fast compilation time, performance-generated code with very minimum side effect. And at the end, I will put everything back to the Mojo compilation context and show some numbers and have some discussion from system design's perspective. All right, just a quick recap on Mojo compilation. So Mojo compiler is built on top of both MLIR and LLVM. We use MLIR to build our front end and the middle end, which is the parser, the elaborator, plus some of the middle end optimizations. Then we use LLVM for the code gen to go to target generated code. We're kind of using LLVM in an unconventional way, in the sense that we parallelize the LLVM pipeline so that we can get fast compilation time, and also we want to guarantee that generated code is performant. This actually significantly helps us to cut down the LLVM pipeline time for the overall Mojo compilation time. So one reason to use LLVM is because LLVM is powerful. It's very good for us to go to target-specific code generation result. There's also a lot of optimizations that we want to use. We don't want to build everything from scratch. LLVM also has a little bit of limitations. The biggest limitation is that the framework is not designed for parallelization. So just like everything is not thread safe. And it's usually a bottleneck for compilation time for systems that's building on top of LLVM. And also some of the LLVM optimizations are kind of unpredictable. There are a lot of heuristics. It's like a compiler magic. It's hard to predict what's the effect. So when we build our LLVM pipeline, we kind of use two principles. One is that we try to simplify the LLVM pipeline as much as possible. So currently, Mojo pipeline only has most of the function level passes, and plus only one IPO pass, that is the inliner. The second part is the main part is that we try to parallelize the LLVM part. The way how we parallelize the LLVM pipeline is that we have the input one LLVM module. We split the module into submodules and run each submodule with its own LLVM pipeline, and we can run them in parallel. We do two levels of splitting. The first level of splitting is that we split the LLVM module into subgraphs, based on anchoring functions. Anchoring functions are external visible functions. And when we split the graph, we will keep all the functions on the function call stack in the same subgraph so that we can run transformation passes, including the IPO passes, and with pretty much get the same effect out of that. And further down, once we finish the transformation, we will split the subgraph further into per function and run codegen in parallel for each function. So if we put this into the LLVM pipeline context on the right side, so LLVM pipeline mainly consists of 4 parts: the front end, the optimization passes, transformation passes, codegen, and then code emission. We don't really care about the front end here because we have our own front end. So the subgraph level splitting is mostly applying on the optimization pass, the second part. And the codegen part is we do per function level parallelization. So this is also from last year's talk, but just like a quick example to show how does this splitting look like with a concrete example. So here we have an LLVM module with 2 external visible functions, for and bar, and 2 internal functions, G and H. G and H are being called by for and bar. At the first level subgraph splitting, we will split the module into 2 subgraphs, one for foo and one for bar. And we will copy duplicated G and H in each of the subgraph, so that we can see the whole function call stack. And further down, when we finish all the transformations, then we will split the subgraph into per function. Here, each function is in their own submodule. And you may also notice that we have to change symbol linkage type for those internal functions into weak, because when we do code generation, we don't want those functions to be optimized away. When they are in their own separate modules, if there's no one's using them and they're also internal, they will disappear. And we don't want that to happen. So this is pretty much how splitting looks like. Once we can do all the splitting, we can run the things in parallel, but eventually we need to put them together. How do we do that? The easiest way is just like run the whole pipeline all the way to the end of code emission. We have object files, and then we put them all together into an archive file. This mostly works fine if we just want to have a binary object, like binary output for a Mojo program, or we just want to send the code for JIT execution. This is a little bit problem if we want to actually generate the assembly output. For example, if we want to do it for debugging or generate the PTX code, it's kind of hard to combine multiple assembly files into one. And one big problem is that we cannot fix symbol linkage type if we are just archiving the code emitted result, because the code has already been generated. This potentially can expose some internal functions as externals. That's not ideal. There's also a duplicated function issue here. So the ideal case would be we have one LLVM module as input, and we want to have just one output, as if nothing happened in between, right? Like parallelization should just be implementation details. It should be a kind of a transient state. And we want to minimize the side effect. Especially for the symbol linkage type change, we want to make sure that it's just internally happening and we don't see it reflected in the output. So essentially, this is a MapReduce problem. For the splitting, we are mapping everything into some modules so that we can run in parallel. We do have to duplicate some of the LLVM context, those things, so that to make sure that even though they are not thread safe, because now each split has their own copy, we can run everything safely. But eventually, at the end, we need to reduce each split into one output. So it more looks like this on the left side. We kind of have to split the code gen pipeline into two parts. It's the code generation and code emission. So we can run the code generation in parallel. We have optimized LLVM module as input for the code gen pipeline. And at the end of the code gen pipeline, we have the kind of machine code result, which mostly are in in-memory data structures. And before we emit the code calling ASM printer, we want to do some reduction. There are multiple ways to do this. More straightforward or logically easy to understand ways to use MLIR. And because MLIR is kind of the serialized format for code gen result, and we can use LLVM linker to link the MLIR. Our experiment and prototyping shows that MLIR is not quite stable for this use case. It's also YAML-based, so it's kind of text-based. It's not quite performant in terms of how to manage these things. So instead of using MLIR, we introduced this new component called MCLink. Basically, we just directly go to manage and manipulate the generated code in-memory data structure for the reduction. Fortunately, there are not too many things that we have to do to manage the reduction. Mostly is we need to do a bunch of uniquing for those global things when we put each split together. For example, the constant pool ID need to be uniqued. And for x86, we need to do uniquing for the PIC-based symbol. That's for the position-independent code-based symbol. And also the MO external symbol need to be uniqued. Basically, just these three things. And then we also need to have the kind of linked LLVM module to guide the ASM printer for the final printing. So we still use LLVM linker to link the submodules, LLVM submodules, into one linked version. And we can fix the symbol linkage type in the linked version that will solve the symbol linkage type change problem. So eventually, we can use this linked LLVM module to guide the ASM printer for the code emission. So more details, we introduced 2 passes for uniquing. Mostly is for the, we can manipulate the machine function ID to unique the constant pool ID and things like that. And we can also try to unique the MC symbol, that is for the external symbol. In addition to that, we actually have to move those private data structures in the codegen result around to all back to one centralized place for the final code emission. In specific, for each split after the code generation, LLVM module have all the code generated information in machine module info for each split, and every function has a machine function, and everything is in the MC context. These are per split. But for code emission, we want to move those machine functions all into one machine module info that belongs to the ASM printer and also has only one MC context for the ASM printer. And then we use the linked version here to guide the ASM printer to do the code emission. Another kind of implementation detail, implementation kind of surprise that we saw is a peak memory jump. So on the left side, on the right side, this is the memory footprint for one of the examples that we're running without MCLink, and on the left side is with MCLink. And you can see on the left side, there's a memory peak memory, like keep increasing and drop at one point. So the main reason of this is because now, due to MCLink, we have to hold all the codegen results together to meet a barrier. Instead of without MCLink, we can just run the codegen, do the code emission, and we can release all those data structures. And we only need to hold the object file buffer to meet the barrier, which is much smaller than the codegen result, the in-memory data structure size. So, but luckily, we figured out why. One of the reasons why this is keep jumping, this is from the instrument result. What we figured out is that in LLVM target machine, it is a mutable data structure, so which means that we have to keep each split has their own copy, but they all share one data structure called sub-target map, which has exactly the same information for every split, because we're compiling for one initial LLVM module and for one specific target. We do need these information for the codegen for each split, but once the codegen is done, we will not need this anymore. We only need one copy for the final code emission. So we can actually release this data structure as soon as we finish codegen for each split. So by doing this, we also try to reduce the duplicate function because we eventually only need one copy of the like a duplicated function, especially for those internal functions. So with these 2 fixes, we can drop the peak memory footprint by about a third, from 2.5 gigabyte for this test case to 1.7. Okay, now let's take everything back to the context of Mojo compilation. Here I'm showing the compilation time for 2 test cases. One is for matmul, one is for conv epilogue. These are the 2 kind of benchmark that we're running internally. It used to be a kind of compilation time is a pain point for development iterations. So we try to really improve the compilation time for these test cases. I'm showing 3 sets of numbers here without any parallelization, with only subgraph parallelization, and with both subgraph and function level parallelization. So the good news is that with parallelization, we can improve the compilation time. So for matmul, we get about 15% speed up, and for conv epilogue, we get about 30% speed up in terms of compilation time. And also, we don't sacrifice the generated code quality. You can see the execution time is still the same as if we don't have any parallelization. The second row is a little bit interesting here. So we are having lower level of parallelization, but here you see that compilation time is faster, and for this case, execution time is slower. My guess is that this is actually not exactly the same as if we have full compilation, because here I have duplicate symbols. For duplicate symbols, to make MCLink work, I have to change the symbol linkage type. My guess is that that affected the transformation path quality, so that we actually run less optimization. That's why compilation time is faster, but the generated code quality is worse. You may also see that maybe the speed up for the compilation time is not so impressive. Mostly it's because now our LLVM pipeline is much smaller compared to the whole Mojo compilation time, because at the same time, we also try to really cut down the IR size. So now, actually, the parser and the more front-end part takes more time in terms of the whole Mojo compilation time. All right, now let's step back to see what do we learn from this practice. First of all, we learned that parallelizing LLVM compilation can really help us to improve the overall Mojo compilation time. This is mostly related with Mojo compilation model, because it's different from C++, right? We usually have a C++ project, we have multiple C++ CPP files, and we compile them into .object files and then try to link them. But for Mojo, we write different things in different Mojo files, and we import them from each other. So once after the parsing is finished, the whole Mojo project is in one compilation unit. So we usually have like the whole world in one compilation unit. That's why parallelization really helps us to speed up the compilation time. And with the help of MCLink, we can parallelize the LLVM pipeline, but have very minimum side effect. No symbol linkage type change, no loss of generated code performance. I wouldn't say it's 100% exactly the same as if we don't have parallelization, but it's pretty close to very, very minimum side effect. And in terms of how we do the threading and parallelization within the compiler does not do too much of the implementation details. We actually rely on our asynchronous runtime to handle the threading. So the compiler just creates different tasks and set up the dependency and send everything into the runtime. So the runtime will decide how to dispatch the workload. In a sense, if we want to control the level of parallelization, we can just control the size of the thread pool for the runtime system to control the level of parallelization for compilation of a single Mojo program. But there's another question of what if in build systems we want to compile multiple Mojo programs in parallel? For example, in a basal system. This is still an ongoing kind of topic that we're trying to figure out the solution internally. Maybe we can use a compiler server or something else. But fundamentally, we need somehow a global supervisor who can see the whole situation and try to decide how to balance the resource and how to do the threading, scheduling, make that kind of decision. For disclosure, this approach has limitations. We've only tested this for x86 and ARM64 backend. This is not really, the function level parallelization is not applicable if the codegen pipeline is interprocedural. For example, NVPTX is not, we cannot really do that for NVPTX backend. We do use the same infrastructure for GPU compilation, but mostly it's at the subgraph splitting level so that we can split the different kernels into different submodules and compile them in parallel. We do not really have the reduced problem for GPU compilation for now. And I also have to use some of the C++ tricks to work off tree, because when I move those data structures for codegen result, those data structures are mostly private and protected members. To move them out of the tree, we have to use C++ loopholes to make that happen. We would love to upstream this. I created 2 PRs, upstream PR. One is for the LLVM module splitter, one is for the MCLink. I would love to have folks to review it to see if it's beneficial for the community, and I probably should write an RFC for this so that we can go through the formal process to upstream it if this is something that people like. So this is kind of how we try to solve this problem without having to do a big surgery on LLVM. It works for us. Is this the best idea? I would like to get more discussion and have feedbacks on how, if you guys have any inputs on this approach. This is all I have. Thank you very much for listening. Any questions?
Thank you. That's very interesting. On slide 17, you have the comparison of compile times. I'm curious, what does the peak memory overhead, if any, would look like?
The memory overhead?
Yeah.
Like something in here?
Yeah, so if you compare the situation where you do parallelization with the one where there's just single LVM handling everything.
That's a very good question. There's definitely memory overhead because we have to duplicate a lot of things, right? Like here you can see if without parallelization, we just have one module and one LLVM context. When we try to parallelize, we have to duplicate the LLVM context. So these are the extra memory kind of pressure we have to put on. And for CodeGen, we actually also have to duplicate the MC context. And here, for the first level subgraph splitting, we also have duplicated functions. So these are all potential memory pressure to put on. It really depend on case by case, how big the module look like, and how much do we have to duplicate.
Yeah. I guess like just interesting for some of those examples where you had the compile times, it would be really great to also have some peak memory comparisons.
Got it. Yes, agree.
Thank you.
Thank you.
Could you comment on the speed up limited to the backend itself? So from what I understand, the numbers that you show here are your end-to-end compile times. So could you comment on the speed up for just the LLVM part of it?
Yes. So yes, this is end-to-end speed up. Empirical data, just based on my memory. Right now, for us, the parser takes about 30% of the overall computation time. The interpreter, which is part of the elaborator, takes close to about 30%. So the backend is about less than 40%. So here, if we look at this 28% overall time, it means that the backend is probably 2x speed up with parallelization.
All right, thank you.
Yeah.